Hi, my name is Emily Rakowski, and I will be demonstrating the von Neumann stability analysis, and I will be demonstrating why the radius r cannot be greater than 1/2. And for this, we have to recall the Euler's equations, which are e to the I x equals cosine x plus I sine x, and e to the negative ix equals cosine x minus I sine x. These will have to be used later on in this to substitute and simplify. And then we can also recall that temperature equals e to the ikx times e to the negative alpha k squared t. And here I'm going to prove that this is true by using the heat diffusivity I never know how to say it. The heat diffusivity equation, which previously we talked about, which is partial derivative of temperature over partial derivative of time equals the constant times second derivative of temperature over derivative of x squared. And here we can plug this in for t on both sides and take the derivative, and once we do that we'll get, and once you do that, then you're gonna get alpha k squared, it'll be negative alpha k squared e I k x e negative alpha k squared t, and that'll equal, so that's the left side, and that'll equal alpha k squared e I x e negative alpha k squared t. Oh, and you're going to have, you also have I squared. So this I squared, so we know I squared is going to be equal to -1, so that'll make this negative. So then these will both be equal to each other, so that proves that this temperature equation is true. And then from here, so let's erase this. Okay. And then we can write this as a summation using Fourier's law. So then t equals summation k negative infinity, from negative infinity to infinity of ck e I k x e negative alpha k squared t. And then you can pull out terms and simplify to get tjn equals e I k delta x, or you need the j delta x, and then e negative alpha k squared and delta t, and this is x equals j delta x, and n equals, t equals n delta t. And recall from the last video that j represents the position and n represents the time integer. They're both integers. And from this you can also rewrite it to make it easier to simplify back into here. You can rewrite the tj plus 1 and the t j minus 1 equations. So when you move that around, the tj, this one is going to be e I k delta x times tjn, and then tj minus 1 and equals e negative k delta x tjn. So that just makes it easier for when we plug back into here. So now we can plug back in, we can plug these in there to solve. So then from here you're going to get, you'll get t j n plus 1 equals t j n plus r times e. I k delta x t j n minus 2 t j n plus e negative k delta x t j n. And then from here you can plug in with the Eulers. You can plug in Euler down here and simplify. Then you'll get tj n plus 1 equals, and then you can also pull out the tj n term to simplify more. So then you'll get a plus 1, and then plus 1 plus r times 2 cosine k delta x minus 2 here. And then you can also pull out the 2 to simplify more. It'll just help when we're looking for the values where r can exist and cannot exist. So you want to simplify more and do tj n plus 1 equals tj n plus 2 1 oops 1 plus 2 cosine k, oh I can't spell, cosine k x minus 1. Okay, so here this whole thing has to be between -1 and 1. So you can do, it would be -1 is less than 1 plus 2r cosine k delta x minus 1 is less than 1. Simplify more. So subtract by 1 on both sides. We'll be left with 2r cosine k delta x minus 1 less than 0. And then -1. So divide everything by 2. -1 r cosine k delta x minus 1 less than 0. So here you can take each term by itself, so you know -1 less than r -2 less than 0. So then here you know r has to be less than 1/2. And then also here, this shows that cosine has to oscillate between -1 and, sorry, I'm writing at the bottom, so my handwriting's kind of bad, between -1 and 1, which we know that that's true from previous. And so basically if r is greater than 1/2, this would cause issues with the stability, because we know how the sine and cosine functions are. So, and basically with this, if this part of the equation is greater than, well, the absolute value of it, if it's ever greater than 1, or I guess not here, I meant here, that I already highlighted, but it basically shows that we can't have a a big delta T or a very small delta X, because it will cause stability issues because R is equal to the heat constant times delta T over delta X squared. And this would also cause this to become very big, and we can't have an approach infinity, which is impossible for a temperature profile. So in the next video, I will be talking about a way where we can have an R that is greater than 1/2. So thank you.